Hi, everyone. Let's say you're brave and you take a trip to Las Vegas. You decide to play roulette. You go up to the roulette table and you see on the roulette wheel 18 red numbers or red slots and 18 black numbers or black slots. Let's say you bet $1 on red. Now, don't laugh. I know that a casino would laugh at you for betting $1, but let's say, hypothetically, you bet $1 on red. Well, if the wheel comes up a red number, or if the ball falls into a red slot, same thing. Basically, if the ball falls into a red slot, it means that that red number comes up on the wheel. Then you win, and you get your dollar back, and you get $1 on top of that. So you win a net gain of $1. However, if the roulette wheel comes up on a black number, for example, then you lose your dollar. You're out $1. Now, is that a fair deal? If you bet $1 on red, if you win, you get a net gain of $1. Is that a fair payoff? The answer is no. Guess what? Casinos are in it to make money. It's not just the players. The casinos are there to make money. What tilts the odds against you? What slightly tilts the probabilities against you? It's those two green slots, 0 and 00. Actually, in Europe, they're nicer because they only have one green slot. But in America, we're not as nice. There are two green slots that could mess you up even more. So why do the two green slots mess you up? Because the total number of numbers that are available on the wheel, the total number of slots on the wheel is not 36. It's not 18 plus 18. It's 18 plus 18 plus 2. And the sum of 18, 18, and 2 is 38. The probability that the wheel comes up red is 18 over 38, or 9 over 19, about 47.4%. Same for black. And the probability of getting a green number, 0 or 00, is about 5.26%. But those two green slots, that tiny percent, slightly tilts the odds against you. It's not a fair game. $1 would not be a fair payoff if the wheel comes up red, because the probability here is a bit less than a half. If you only had the 18 red slots and the 18 black slots, then a $1 payoff would be fair for a $1 bet if you bet on red, because then the probabilities would be 50-50, 50% versus 50%. But actually, in order for this to be a truly fair game, we'll see this later on when we talk about expected value. If you bet $1 on red, then really, because of this percent that's a bit below 50%, a fair payoff would actually be more like $1.11. The casino pays an even money payoff for red-black bets. In other words, every dollar bet is matched by the casino if the player wins. But this is slightly unfair to the player, to you, because a fair payoff would not be $1, it would be $1.11 for every dollar bet. But see, the fact that the payoff is only $1, that ensures that the casino makes a profit in the long run. And what ensures that? It's something called the law of large numbers, what I'll call the LLN. The idea that probabilities built into the game will crystallize in the long run. So in other words, the observed relative frequencies of red, black, and green results, if, for example, imagine a gambling addict were to play this game 1,000,000 times, all right, then you're going to pretty much see these probabilities come up as relative frequencies. The relative frequencies will be very close to the theoretical probabilities in the long run, that is, over many plays of the game, say 1,000,000 plays. Again, the observed relative frequencies over like 1,000,000 plays, okay, of red, black, and green results will approach the corresponding theoretical probabilities. These in fraction form, these in percent form. So in the long run, over 1,000,000 plays, you're going to see about 47.4% red numbers come up, about 47.4% black numbers come up, about 5.26% green numbers come up. All right. So in the long run, on average, the casino will make a profit of about 5.26 cents for every dollar bet made by players who bet on either red or black. And that comes from the fact that there's about a 5.26% chance that the roulette wheel will come up green as opposed to red or black. So we call that the house advantage. It's 5.26%. In fact, it turns out that it's not just for one number. If you bet on groups of numbers, this is often the kind of house advantage you see for roulette for various types of bet. All right. Now think about this. What is the best way to maximize your chances of winning a huge amount of money in Vegas, in any game? Given that in the long run, the probabilities are meant to work against you. In the long run, the probabilities are meant to work against you. The probabilities will crystallize in the long run, and the payoffs are set against you in the long run. How do you maximize your chance of winning a huge amount of money? You need $1 million to pay someone off. What's the best way of doing it, probability-wise? Yeah, I think the best way of doing it, put it all in one shot and hope. Really, really hope. Now, speaking of the law of large numbers, here's an example with coins. These are computer simulations of coin flips, assuming a perfectly fair coin. The law of large numbers guarantees that theoretical probabilities will crystallize in the long run in the observed relative frequencies. The observed relative frequencies from repeated trials, like 1 million trials or 1 billion trials. Think of 1 million or 1 billion plays in Vegas. Okay. The LLN says that the observed relative frequencies will approach the corresponding theoretical probabilities as the number of trials approach infinity. So over many years, the casinos expect to make money. Donald Trump critics will joke otherwise. In each column below, we simulate the flipping of a fair coin, in the red column here and the blue column here. So if we first consider 10 flips, then 100 flips, then 1,000 flips. Again, these are computer simulations of a fair coin. So for example, in simulation 1, so a fair coin is flipped once, it comes up tails. In the vertical axis, that describes the relative frequency of heads. So if you flip a fair coin, all right, let's say it comes up tails, then you've gotten 0% heads so far. If you flip the coin again, the computer flips the coin and it comes up tails again. So far, again, 0% heads. But then the computer flips a head. 1 head out of 3 flips, the relative frequency of heads so far is 1/3. So we're tracking the relative frequency of heads so far. Then the computer flips the coin again, gets another head. 2 heads out of 4 flips, the relative frequency of heads is 1/2 or 0.5. And so on. Now look what happens after 100 flips of the coin, and then 1,000 flips. It looks like the relative frequency of heads is really approaching what number? It looks like it's really approaching 1/2 or 0.5. It's approaching this flat line. The law of large numbers says that in the long run, the observed relative frequencies will crystallize towards the probabilities. The probability of a fair coin coming up heads, by definition of a fair coin, is 1/2 or 0.5. The relative frequency of heads will approach 0.5 in the long run. Okay. Here's another simulation. It's a repeat. Well, it's a repeat of the idea, but the computer flips the coin 10 flips, 100 flips, 1,000 flips. Now we're getting a different sequence, but still in the long run, we're getting about 50% heads in the long run, even though the particulars are different compared to the red simulations. So again, in the long run, the law of large numbers says that the observed relative frequencies will approach the theoretical probabilities.